This is going to be a short talk on applications of K-mers. And yesterday I gave a warning. If you are familiar with K-mers, or if you invented K-mer Bioinformatics, this is going to be too basics for you. too basic. This is really...
That's what I like.
Well, you'll see. It is essentially K-mers for the CGSI part that doesn't know too much or at all about K-mers. It's going to be the most basic things ever, hopefully. Let's get started. You have some biological material that you sequence using a certain black box machine, which ends up being a collection of reads. And from these reads, you can extract K-mers. And let's get into this. We start with two reads. Read 1 and read 2. And these are going to be a CTCA and GTCA. Handwriting okay so far? Excellent. There's one operation that is commonly referred to as K-mer counting. I need to write from this angle. Which consists when you have set a certain k length. Here it's going to be k equal to 3 for the purpose of this example, but in real life, as you saw in previous talks, it was much larger k values, but here I want to have small ones. You can essentially enumerate all the strings of length 3 from your reads. So we can start ACT, CTC, TCA. That's all from read 1. Then we can start with read 2, GTC, and then we see TCA again. And if we want to just enumerate all the K-mers and not have duplicates, we'd stop here with the enumeration because TCA is already seen here. The counting in K-mer counting consists of creating a table where you actually count how many times you see each K-mer from the reads. ACT is seen only once. CTC, 1. TCA, twice. GTC, 1. So that's K-mer counting. Seems very easy from this small example, but imagine you have billions of reads. This becomes a computationally challenging problem. Then, from this table of counts, there is such a thing called a K-mer histogram. Which consists of taking this table and essentially reporting, forgetting about the sequences of the K-mer themselves, but just looking at the distribution of values here. So here there are only two different values, 1 and 2. And there is and then you count how many times you see 1 in this table. You see it 3 times. How many times you see 2? See it twice. You see it 1. From this example, there is really not much going on. The K-mer histogram looks like this. Let's make it slightly more interesting, and assuming that you have a third read that is strictly identical to the first one. How does this table, how does everything change? The set of K-mers stays exactly the same, right? However, this table changes. ACT becomes 2. CTC becomes 2 as well. TCA, 3. How does the histogram change? Well, now 2 becomes a 3 here. You've got a 2 here and a 1, like this. If you keep repeating the operation I just did, which is repeating this sequence, what is going to happen? K-mers remain the same. You're going to increase here. In terms of the histogram, things are going to get shifted to the right, except for this one little K-mer here that is never going to appear again. The biological interpretation of this read is that it could be a sequencing error of this particular base, which leads to the creation of one K-mer GTC that is only going to be seen once. And it's going to stay here. Everything else is going to shift to the right. And this particular value here, which is a 3, not grouped with the rest of the 2s, it's because there is, well, this K-mer that is appearing just one more time in a sequencing error containing read. So where I'm going at is that in actual sequencing data, what you typically observe are K-mer histograms which look like this, where this region corresponds to K-mers which contain errors, sequencing errors, and this region corresponds to K-mers which correspond to from the actual genome that you sequenced. Abstracting a few things here, because this, when you have deployed genomes, it doesn't look like a perfectly nice normal curve. It looks like actually a mixture of two due to heterozygous and homozygous K-mers. I won't go into these particular details for this example, but hopefully this is illustrative enough for you at the moment. Zara, you seem to be, are you fine? Okay, great. Any questions? So far, so good? Okay, great. Let's complicate it a tiny bit, but not too much though. I'm gonna erase the whole thing. I don't want to keep crouching. This is one sequence, one read, ACTG. From a read, you can do the same thing as we did before and enumerate K-mers, but we'll go one step further. We'll construct what is commonly referred to as a De Bruijn graph. And the De Bruijn graph is a graph which has a set of nodes and a set of edges. The set of nodes are just the K-mers. Still K equal to 3. For the specialists in the audience, I'm going to just mention, for the sake of the video, that I'm considering a node-centric De Bruijn graph. And this particular definition, edges correspond to exact K-1 overlaps between K-mers. So far, so good? Yes? It's slightly easy example here. Let's complicate things a little bit more, and instead of this read, we'll make it a bit longer. Oh, no, we'll add more reads. So CGSI and one more TCGT, GCT. If you have this collection of reads, the Bruijn graph no longer looks like this. You have to add a few more nodes. Can you spell the rest, please? What do I write here? TGC, thanks. GCT. Yes. Anything else? That's it, right? Yep. I forgot a few things, like the edges. Since you have the same K-1 sequence here, you have an edge. Same here, have another edge. Okay? I'll move that from the way. This is a particular sequencing data set, but in practice what happens is you often see the same region of the genome in multiple reads. So if you, for instance, duplicate some of the reads, have different read length, and make it a little bit more realistic, you would have those reads. What needs to be changed from the De Bruijn graph to now have the De Bruijn graph of those reads? More edges. It's really tempting to say, since I've seen this beginning twice, I could put another edge here. But in practice, this is a good observation. In practice, a graph, in mathematical sense, only has one edge between the two nodes, if they are connected by already one edge, you don't have another edge. What you are thinking about is a multi-graph. That's not the case here. We will not add more edge. What people might be wanting to do is have also an annotation on the edge. We will do 2 here. In practice, this is sometimes done, but it's also interesting to maybe record the number of times you see a K-mer on the nodes. So you could have 2 here, and here actually much more than 2, something like 4, I think. So these are all annotations to the graph, let's say, but they don't change the structure of the graph itself. So if you were disregarding annotations, this graph would have been exactly looking the same for this data set as it was for the restricted data set. Okay, we're making progress now. Let's add one more read. CTGA. If we add this one, what changes? One more K-mer. Let's write it here. How does this connect to the rest? Here. And I realize now from my notes that have been misleading you the whole time. The graph is actually wrong. How wrong is it? Not one edge is missing. And nobody shouted. This was, of course, a test. Yes, this little edge here. Because why is it missing? Because this part, CT, is a K-1 overlap with the next K-mer here, CT. You were not paying attention, or you were thinking I was right, but I was not.
It's immediately clear because 2 doesn't equal to 4.
2 doesn't equal to 4.
There are 2 incoming catches, and the degree of the node is 4.
The number of times you see this, you mean?
Yeah.
Oh, yeah. Ooh. I'm
Do you put convention space at all?
I myself, I typically don't.
Yeah, it's kind of like, you can compute it just for those.
You can, ooh, not clear, because like, for instance, if you had this read, CTG alone, it would have increased the weight of this node, but wouldn't have changed the topology of the graph. So there is. But anyway, the point was that something was missing. and we kind of didn't find it soon enough. So now, from the topology of this graph, there are 2 potential situations going on. Remember, we are sequencing a genome. So how do you perform genome assembly, which is reconstruct the sequence of the genome from the graph alone? You don't need to really, you either know this or you don't, I guess, but it's tempting to say that the genome must contain all the K-mers inside from the graph, and it's also tempting to say that the genome is a path inside this graph that contains not only all the nodes, but also satisfies the constraints of the edges. So there has been, I'm gonna very quickly brush over decades of assembly research, so this is gonna be disappointing for some specialists here, but my only remark about this graph is that there can be 2 potential situations. One is that the genome is a path that goes like this. The other is that this edge that was conveniently forgotten until now corresponds to a spurious edge that just happens to be a repetition between this part and this part, and that the genome is actually just this. And this would be just a sequencing error. From the graph alone, from the limited amount of sequencing data we have, it's very difficult to actually know what is going on, which one of the 2 situations it is. And this is typically the intrinsic reason why assemblers have difficulty in assembling genomes at small k value, for instance, or even normal k values. But this is more like an aparté. I'm gonna now add a few more reads to this. I've already added I'm going to add TGAT. And if you add this, you add just one K-mer. Does this overlap with anything else? No. Now when you add this read, it kind of reinforces the confidence that this was not a sequencing error, but rather part of the actual genome. And now it's more likely that the genome follows a path like this. So essentially the lesson here is that when you have isolated K-mers, there's always a possibility when they have low count that it's a sequencing error, but the fact that it is now linked in a path, a longer path than before, decreases the probability that it is a sequencing error. And this is kind of a property that is used in genome assembly software. Yes?
I'm confused. Why there is an edge between GCT and CTG? I thought edges are only included if there is GCT in the reads.
Oh, yes, yes, yes. Okay, so excellent question. There is the concept in the literature of two different definitions of the Bruijn graph. Node-centric and edge-centric. Node-centric is you enumerate the K-mers and then don't look at the reads anymore and find edges using only the information from the edges. Edge-centric is perhaps the definition that is more historic, where you draw edges when there is real evidence that not the k equal to 3, but the k equal to 4 is present in the reads. So that's kind of two different ways to construct the Bruijn graph. They are not equivalent for a fixed k because of what you said. For instance, I think you mentioned that GCT and CTG shouldn't be linked because there is no read evidence that contains GCTG. Not here.
Well, this approach is less relevant to assembly, right?
Both of them are. And you could think that it's better to actually link K-mers because because there is evidence from a read, so you are less likely to have misassemblies. But this only shifts the problem for when you have a no longer K-mer but K plus 1 mer. Maybe I don't want to go in. I mean, maybe I can go into a little tangential here, like this additional evidence that you would perhaps remove this because it is not seen in a read shows up again if you consider paths not of length 2 but of length 3. So essentially, adopting the edge-centric approach doesn't solve all of your problems. It only shifts the problem by one more base. It has been kind of studied in a few papers that these two formalisms are not equivalent, but fundamentally capture the same information if you shift the K-mer size by plus or minus 1. So in practice, my main message is that when we do assembly in a node-centric way, you are not immune from this type of problem, but in the general sense, you get assemblies which have the same quality as if you had edge-centric, the Bruijn graph, because you're just shifting the problem one less base or one more base. And the choice of k is essentially going to be much more dramatically influencing than the choice of the method here. How much time have I spent on this parenthesis? Too much. Okay, let's get going a little bit further. I'm going to just briefly mention one aspect that has been completely ignored until this talk, which is reverse complements. So when you sequence DNA, you can either sequence from this orientation or this orientation. And essentially what happens is that a K-mer AAC, when you sequence it from a read, it could have been very well be GTT. And the way this is represented inside actual Bruijn graphs is that we have this kind of nodes which assimilate a sequence in a forward sense to its reverse complement. And this kind of makes things a little bit more complicated now because assume you want to actually draw the Bruijn graph here, what is happening is that if you draw a simple edge, it's better to actually annotate the edge saying forward, forward. And another edge, reverse one, which is reverse, reverse. Because this connects with this. The complication comes from the next K-mer, which is going to be, assume you have CCT, which would be the following here. Reverse complement would be HGG. And now what do we do? You still want to write an edge, but drawing this way is kind of confusing. It's actually better to draw it this way. And annotate it FR. And then you have the reverse edge. How is it annotated? It's also FR, because this is F and this is R. So that's all I want to say about reverse complement. This doubles kind of the complexity of the graph, but it doesn't really change much apart from this representation being a little bit more burdensome. That's why in most assembly papers, in most K-mer papers, you never see this being presented, but behind the scenes, in the software, this is actually what's being performed. Okay, I have 5 more minutes. I want to briefly touch upon a final topic. Now suppose you have 2 individuals. And both of these individuals have very short sequences, ACTCA. And GTCA. There's one object that is being increasingly interesting, is the object of a K-mer matrix. Where you do exactly the same thing as I did before. You enumerate all K-mers for a certain size. And now, instead of counting this as a unified set of reads, you actually differentiate between individuals. Now what do I put here? 1, 0. Okay, you got it. 1, 0, 1, 1. 0, 1. And now the interesting thing about it is here it's only 2 individuals, but if you had way more columns, a bigger sample size, you could actually run statistical tests on each row of the matrix. Because really, here you could say this particular position, I don't really know what's on the left of this individual, but this could be very well a SNP. And this SNP is reflected by not 1, but 2 K-mers. And this happens to be, well, it's actually reflected by not 2 K-mers, but also this one, because it contains this particular C. And this is the alternate allele. And these rows happen to be the ones where the counts are not the same between the individuals. So if you had more statistical confidence by having more individuals, you could actually detect them. And by detecting them, you would essentially be able to run GWAS. This row is not very interesting because it contains K-mer seen in everybody. This is related to the talk you saw earlier this morning, where essentially Julia is removing this stuff and keeping this stuff. And in fact, if you like this type of objects, we have a tool called Kmtricks that constructs this matrix efficiently for large number of individuals. And we have another tool called mdiff that I was presenting in my talk briefly yesterday that takes this matrix and runs a GWAS on it. And it was able to run for large amount of human individuals. So it can take billions of rows and thousands of columns. And I think, given the very short time of this session, I'll stop here and take any questions. Thank you.